Next, we will have more discussion on the vaporization, boiling, melting, and freezing. Okay. For boiling, it's a process in which a pure substances change phase from liquid to gas. Okay, all of you should know. And for melting, it's a process from solid to liquid. Okay. And we will also describe the temperature of melting as also boiling by melting point and boiling point. For melting point, is the temperature at which melting occurs at certain pressure in a crystalline substance. Okay. I just talked about crystalline substance because amorphous substance has no sharp melting point. Okay. Let me explain a little bit what is crystalline, what is amorphous. Crystalline means the substance has a so-called long-range order. That means the substance is well ordered. For example, if you have a piece of metal, then we would say that this is a crystalline substance because inside the metal, all of the ions have a very well-ordered structure. But for amorphous, because they do not have a very long-range order, they just have a very short-range order. For example, if you cool down the melted glass very quickly, then all of the molecules would have a sudden stop at some places. Okay, and this kind of stopping would make the molecule to be placed in a disordered manner. So we say that the glass has an amorphous structure. Okay, and for amorphous structure, due to their very short range order, they do not have a sharp melting point. Okay, because in order to have a sharp melting point, that substance should have a very average intermolecular force. Okay. For the case of amorphous substance, because at some places the atoms are packed very closely, so the intermolecular force will be extremely strong. But at some places, the intermolecular force will be weaker. So if you would like to melt the substance, the weaker intermolecular force will be overcome first, and then the stronger intermolecular force. So they have no sharp melting point. And this melting point generally depends on pressure. If the pressure increases, then the melting point will decrease. Okay. For example, if you are skating on ice, you can see that the ice melts beneath the blades. Okay. After you have skating for some time, if you look back to the path, you will see that some liquid water would appear. This is because during skating, your blades have exerted a high pressure to that surface of ice. So that ice has become liquid water because it has gone through a melting process. Okay. For freezing point, it's a process of a substance which changes phase from liquid to solid. That's exactly the opposite of melting point. And it generally equals to the melting point, just generally, because there are some exceptions. For example, agar. Agar would melt at 85 degrees C, but if you cool down the agar will solidify at 35 degrees C. So you can see that in this case, the freezing point will be different from the melting point. But in most cases, in our thermodynamics problem, the melting point will generally equal to the freezing point. Okay. I mentioned the exception to remind you that you shouldn't take for granted that the melting point is equal to the freezing point. Okay. But for most of our thermodynamic problems, we would consider this to be true. Okay. And here is the what we so-called melting curve. Here we have the liquid vapor saturation curve. The P set is plotted against the T set, and you can see that we have an increasing trend. But for melting curve, we have a reverse trend. That is, if we increase the pressure, then the melting temperature would decrease. And from this diagram, we can see why ice skating would make the ice melt. Suppose the temperature is a room temperature, for example, about 300 K, then the pressure will be a bit low. If you add pressure, for example, I just pick a point, but for 300 K, because it's not in this diagram, so I just pick another point, for example, 265. Suppose the original pressure is this position. If you add pressure, then it will suddenly jump here to the higher pressure place at the same temperature. So it changes from solid to liquid. Okay? Okay, for this melting curve, although all kinds of pure substances we have the same trend, but the values are different. The values actually can be obtained for some substances in the property tables. Okay? In our appendix, we will have two kinds of pure substances, water as well as refrigerant 134A. Okay, you can obtain the values of saturation pressure if you have given the saturation temperature and vice versa. Okay, and for other kinds of pure substances, you need to go to other tables. Okay, either you search from the internet or you go to the library to look for the property tables. Okay. Here we will talk a little bit about latent heat. What's latent heat? Latent heat is the amount of energy absorbed or released during the phase changes without change in temperature. It is termed as heat because we need a surface that has a temperature. For example, the latent heat is describing the process where it changes from liquid to gas, for example. So the heating surface must have a temperature that is well above boiling temperature, such that heat can be transferred to this liquid to change it to gas. Okay, and we have two kinds of latent heat: latent heat of fusion and latent heat of vaporization. Okay, fusion just means freezing, so it means the amount of energy absorbed or released during melting or freezing. Okay, well, you can just substitute the bracketed words to this word, okay, because we have seen that during melting or freezing, the path traced is exactly the same, but in the opposite direction. So the magnitude is still the same. Okay. How about vaporization? We have a latent heat of vaporization or condensation. That is the amount of energy absorbed or released during vaporization or condensation. Again, because we can exactly trace the same path in the opposite direction during the heating in the constant pressure process. So that's the case. And this value depends on the temperature or pressure that the phase change process occurs. Okay, if we have different pressure or different temperature, then these values will be different. Okay, for example, at 1 atmospheric pressure, the latent heat of fusion water will be about this value. Okay, 333.7 kJ per kg, and the latent heat of vaporization will be much greater, 2256.5. And sometimes we may also talk about a term called the specific latent heat. Specific means per unit mass. Sometimes here we have the term in a unit mass basis, and this one also. So actually, these two terms should be termed as the specific latent heat instead of the latent heat.